Okay, we're going to move on to alternating currents. So I wanted to be able to show you some of the stuff that we would have done in person. This is a CRO. We'll be using the CRO as a voltmeter because it allows us to see what's happening. CRO has a little electron gun inside it that shoots its electrons at the screen, which causes it to phosphoresce, and you can see what's happening here. At the moment, it's not connected to anything because I wanted it on a zero line. It's a bit like a graph screen. You have a x-axis and there is a y-axis. I will tell you what the scale is or the divisions on that when we get to looking at my DC circuit. So we are going to start off with a DC circuit, but you are seeing it flash. It does flash in person. We might find as I do these videos that the shutter speed of the camera matches too well or doesn't match, and it means that we'll see more flashing than we would see in person, or we might not see the whole patterns that we would see in person. Definitely probably when we get to rectification in the next video. So at the moment, not connected. If I connect it to my DC power supply, assuming there is no interference, I get a straight line. We should have noticed that it's moved from the zero up a little bit. The circuit I have set up, you can see a little bit of a battery poking out here. I've got it across two batteries, so that's 3 volts. I've got my bulb in series with the batteries, and then you can see my little crocodile clips here going to the CRO. This is this circuit here, so you can see the circuit diagram. Direct current goes around in a circle. So big end of the battery is your positive end of the battery. Current is just flowing all the way around. The electrons are going in one direction. Reminder, electrons flow in the opposite way of the direction, but current is positive to negative. When we look at that with an oscilloscope, I've got my y-axis is set to 2 volts per division. That means every little square, not that you can see the squares, is equal to 2 volts. And then my x-axis is equal to 10 milliseconds per division. Not that it really matters with a direct current for now, but just so you know. So when it's hooked up, I get this. So again, it's moved from 0 up. It's actually moved up about 1 1.25 squares. So that's, every square is worth 2 volts. So that is 2.5 volts, hopefully. That's direct current. We actually don't care about direct current anymore, or for this particular topic, because it's alternating current. But that is a reminder of direct current for you. Nice straight line all the way across, as the electrons have the same current, the same voltage as they go around in the same speed, in the same direction. Current is the other way, but whatever. What we're going to do is, instead of using the batteries, I'm now going to hook it up to my AC supply over here. Batteries can go away. And I have an AC supply. Now you can see that it's no longer a straight line. We had a sinusoidal curve, up and down motion, up and down motion. Now I have this circuit. So rather than having a battery, I have an AC supply up here. This is the symbol for an AC supply, dots, dots, and a sinusoidal curve in there because I get a sinusoidal curve on here. What the electrons and what the current are doing in an AC supply is they're oscillating. They're not moving around in one direction, they're instead going back and forth, back and forth, back and forth. So that then gives us this curve here. I'm going to add that onto here. Curve, curve, curve. So what's happening when the electrons are moving? You get a peak when the electrons are at their maximum amplitude of their oscillation. So when they're doing that, so they're oscillating back and forth, a peak is when they're here or here. That would be them in their equilibrium position. When they're crossing their equilibrium position is when you get 0 volts here. So peak is maximum voltage, equilibrium position is 0 voltage, other way, back and forth, back and forth. So your electrons are doing that. They're not moving around the circuit, they're just going back and forth, and you get a sinusoidal shape of graph. The way that we get the electrons to do this is to do an AC generator. I just wanted to look at the AC generator and where the coils are compared to when you get your max and your zeros on your oscilloscope, because I know it can be confusing. It's remembering that Faraday's law of induction is the rate of change of magnetic flux is the size of induced EMF. So when you have a peak, it's my coil of my generator here. I've got a pink side and a green side just so we can relate where the coils are. When you have a peak, this coil is actually horizontal. It's parallel to the field lines. So there's no cutting going on at the moment with a peak, but it's rate of cutting that matters. So when I go from 0, I suddenly can't actually cut it because it's string, but I'm getting a big change in flux linkage. So I go from 0 and suddenly I've hit a flux line and my change is pretty large. When I'm at 0, that's when you have the maximum flux inside my coil, but as it turns, it doesn't cut any more flux. I haven't got a big change in flux. I've got lots of flux inside my coil, but my change in flux actually doesn't really get anywhere until I get horizontal again. So that, when it's perpendicular to the magnetic field lines, is actually when you have 0 induced EMF. When it's horizontal or parallel to the field lines, that's when you have your maximum EMF. The coil, can't really do it on this because they're not real field lines, will turn around in a circle. It's an AC generator, so you are physically moving it. A DC motor was the current made it move. AC generator, you move it, you get a current. So here you can see the blue, it goes there, flaps around, flips around, flips around, keeps going. If we were to right-hand rule that, so the movement is for the blue, I'm going to move it up. The field, I'm going to say this is the north side of my magnet. My current is pointing towards me, you can't see. So when the blue is in this orientation, current is flowing that way, towards the black. There we go. So there'd be like no current, which is when I get 0. Then here, the blue is now on the other side. Field is still that way, blue is moving down. I've now got current flowing down my blue towards me. So what I've had are the electrons being made go this way, still that way. That's an alternating current. I get it from my AC generator. So I have my alternating current here. Same settings on my oscilloscope, I haven't changed them. So my Y settings are 2 volts per division. My X is 10 milliseconds per division. If I take some readings, the peak on here, I know you can't see the squares, but the peak is 2 squares up from 0. So my peak is going to be 4 volts. My trough on the other side is also going to be negative 4 volts. So my peak is 4 volts on that. I have no idea if you can see the numbers. I'm going to mess with this. Ooh. Let's make it still. From peak to peak, which would be a time period, 1 full oscillation, so you can't see the full patterns. 1 full oscillation is 2 squares. So from here to there was 2 squares, or 2 divisions. It's 10 milliseconds per division. That's going to be 10 milliseconds times by 2. My period is 20 milliseconds. So I have a period of a wave. I can find it from a CRO. I'm pretty sure, I don't recall them ever asking you to use CROs again. You still need to know what a period is. You will do it from a graph the same way we have with SHM, the same way we have with anything else where we've had graphs and we've had to find periods. They don't tend to do the whole milliseconds per division, the year 12 stuff, but just in case, same thing. You have a scale, you times it by. So my period of this wave, T, we said was 20 milliseconds. If I know my period, I could find out my frequency. So frequency equals 1 over T. So it's going to be 1 over 20 times 10 to the negative 3. And I get an answer of 50 hertz. Which is not the frequency that's coming out of my power supply. Don't know what's going on there. I kind of eyeballed the period, so it could be that. The answer we should have got, and if I'm honest, most of the answers, when you're asked to find the answer of an AC power supply, the answer is going to be 60. It could be 50 sometimes, but 60 is what comes out of our plugs, and 60 is what I sent mine onto because I wanted to find 60. Close enough though. So 50 hertz power supply, but it's the sinusoidal curve. So we know that sinusoidal things have an equation. Similar equations as the ones we did in SHM. So you can have, we're just going to say x on the y-axis, very handy, and time on the x-axis the way that we usually do. If you remember our SHM equations, what the equation is going to be of this sine graph is it's going to be x equals xo sine omega angular frequency t. XO, if we remember, is the peak. Doesn't matter which peak, positive or negative, XO is your amplitude. So you get XO sine omega t. We also, though, if we remember, omega equals 2 pi f. So if we know x equals XO sine omega t, that means that x equals XO sine 2 pi ft. Little t because it's the time that you get this displacement, not period, time that you would get specific displacement. So you can use this to find your specific displacement at whatever time. So there's two different voltages or currents that we care about. We've used X because one, this, what I have is voltage, so I've got V equals VO sine omega t. I could have current. I'm not sure if there's anything else we can measure there, but definitely voltage and current. It could be either, so X just says that it will work with both voltage and current and anything else that it might be that my mind is blanking on. So XO sine omega t. That is the equation of this graph, so you can find the voltage at a specific time and use it from that. There's two different voltages that we care about. So there's this peak voltage. This isn't what we talk about when we say that, so the Cayman Islands power supply is 110 volts. That isn't your peak. That's something known as your RMS current, or your RMS voltage, because I'm talking about voltage. Your RMS, root mean squared current, is, it doesn't matter which way the electrons are moving in through this resistor. They're moving that way, they're moving that way, they're moving through resistance, so I get power loss. I get the bulb heating up, I'm losing energy. It doesn't matter if they're oscillating to the left or to the right, I'm getting some power loss. So I can use then that power equations, or we're going to do this in lesson, P equals I squared R, that will make the I flip up, and I can find like my average sort of power, and I get, or my average current or voltage, I get a line here. This is known as my RMS. Your RMS current, your RMS voltage, is the same value of what when you would have a DC power supply that would give you the same power losses or the same thermal energy transfers. We'll go through the maths of that. It's basically, yeah, we'll go through the maths of that in lesson. But that's what I wanted to show you with this, and then we'll go through the PowerPoint in class.